implied in this discussion is context length also. Is there a lot of innovations that's possible there?
I think the colloquially accepted thing is that it's a compute and data problem where you can, and sometimes like small architecture things, which is like attention variance. So if you have, we talked about like hybrid attention models, which is essentially if you have what looks like a state space model within your transformer, and like those are better suited because you have to spend less compute to model the furthest along token. And I think that, but those aren't free because they have to be accompanied by a lot of compute or the right data. So how many sequences of 100,000 tokens do you have in the world, and where do you get these? And I think it just ends up being pretty expensive to scale them. So we've like gotten to pretty quickly to like 1 million tokens of input context length. And I would expect it to keep increasing and like get to like 2 million or 5 million this year, but I don't expect it to go to like 100 million. That would be like a true breakthrough. And I think those breakthroughs are possible. Like the continual learning thing, I think of it as a research problem where there could be a breakthrough that just makes transformers work way better at this, and it's cheap. Like these things could happen with so much scientific attention, but turning the crank, it'll be consistent increases over time.
I think also looking at the extremes, I think there's again no free lunch. So the one extreme to make it cheap, you have let's say an RNN that has a single state where you save everything from the previous stuff. It's like a specific fixed size thing, so you never really grow the memory because you are stuffing everything into one state. But then the longer the context gets, the more information you forget because you can't compress everything into one state. Then on the other hand, you have the transformers, which try to remember every token, which is great sometimes if you want to look up specific information, but very expensive because you have the KV cache that grows, the dot product that grows. But then, yeah, like you said, the Mamba layers, I mean, they kind of have the same problem, I would say, like an RNN, you try to compress everything into one state, you're a bit more selective there. But then I think it's like this Goldilocks zone again. With Nemotron 3, they found like a good ratio of how many attention layers do you need for the global information where everything is accessible compared to having these compressed states. And I think that's how I think we will scale more by finding better, let's say, ratios in Goldilocks zone, like between like computing, making it cheap enough to run, but then also making it powerful enough to be useful. And one more plug here, the recursive language model paper, that is one of the papers that tries to kind of address the long context thing. So what they found is essentially instead of stuffing everything into this long context, if you break it up into these smaller, multiple smaller tasks, so you save memory by having multiple smaller calls, you can get actually better accuracy than having the LLM try everything all at once. I mean, it's a new paradigm. We will see, there might be other flavors of that. So I think with that, we will still make improvement on long context, but then also like Nathan said, I think the problem is for pre-training itself, we don't have as many long context documents as other documents, so it's harder to study basically how LLMs behave and stuff like that on that level. Like
there are some rules of thumb where essentially you pre-train a language model. Like Olmo, we pre-trained at like 8K context length and then extended to 32K with training. And there's some rules of thumb where you just like essentially doubling the training context length takes like 2x compute, and then you can normally like 2 to 4x the context length again. So I think a lot of it ends up being kind of compute bound at pre-training, which is in this, like we talked about this, everyone talks about this big increase in compute for the top labs this year, and that should reflect in some longer context windows. But I think on the post-training side, there's some more interesting things, which is as we have agents, the agents are going to manage this context on their own, where now people that use Claude Code a lot dread the compaction, which is when Claude takes its entire full 100,000 tokens of work and compacts it into bulleted list. But what the next models will do, I'm just not a novel, I'm sure people are already working on this, is essentially the model can control when it compacts and how. So you can essentially like train your RL algorithm where compaction is an action, where it shortens the history. And then the problem formulation will be, I want to keep the maximum evaluation scores that I have gotten while the model compacts its history to the minimum length, because then you have the minimum amount of tokens that you need to do this kind of compounding autoregressive prediction. So there's actually pretty nice problem setups in this where these agentic models learn to use their context in a different way than just plow forward.
One interesting, also recent example would be DeepSeek version 3.2, where they had like the sparse attention mechanism, where they have essentially like a very efficient, small, lightweight indexer, and instead of attending to all the tokens, it selects, okay, what tokens do I actually need? It almost comes back to the original idea of attention, where you are selective, but attention is always on. You have maybe zero weight on some of them, but you use them all. But they are even more like, okay, let's just mask that out, or like not even do that. And even with sliding window attention, Olmo, that is also kind of like that idea. You have that rolling window where you keep it fixed because you don't need everything all the time. You occasionally, some layers you might, but it's wasteful. But right now, I think, yeah, if you use everything, you're on the safe side. It gives you the best bang for the buck because you never miss information. And right now, I think this year will be more also the year figuring out, like you said, how to be more smart about that. I think right now people want to have the next state of the art, and the state of the art happens to be the brute force expensive thing. And then once you have that, like you said, keep that accuracy, but let's see how we can do that cheaper now, like tricks,
Yeah, all this scaling thing. Like the reason we get the Claude 4.5 Sonnet model first is because you can train it faster and you're not hitting these compute walls as soon, and they can just try a lot more things and get the model faster, even though the bigger model is actually better.